Hey guys, in this video we will be going over rational exponents. So let's start with explaining the relationship between radicals and rational exponents. So if we have a rational exponent expression like a to the m over n, where m and n are positive integers, and m over n is in simplest form, then we can rewrite this in radical form as the nth root of a all raised to the m power, or the nth root of a to the m, where the denominator of the fractional exponent is the index of the radical. So sometimes converting between these two forms makes it easier to simplify the expression. So let's try a few examples. We want to write the following in radical form and then evaluate. For the first example, since we have a rational exponent, we know that this can be written in the following forms. Therefore, we can rewrite this as a radical with an index of 3 raised to the first power. And since anything raised to a power of 1 is just itself, we can just write it without this exponent. And now we just have to find the cube root of 8, which is 2, since 2 cubed is equal to 8. Therefore, 8 to the 1/3 power simplifies to 2. We can do the same thing for the next example and write 49 to the 1/2 as a radical with an index of 2 raised to the first power. And again, since it's raised to a power of 1, it'll just be itself. And now we are just finding the square root of 49, which is 7. For 25 raised to the 3/2, we rewrite it as a radical with an index of 2 raised to the 3rd power. So the square root of 25 is 5, and then 5 cubed equals 125. And we can rewrite 64 raised to the 2/3 as a radical with an index of 3 raised to the 2nd power. So the cube root of 64 is 4, and then 4 squared is 16. 1000 raised to the 2/3 can be written as a radical with an index of 3 raised to the 2nd power. So the cube root of 1000 is 10, and then 10 squared is 100. Okay, so now let's try some examples with some negative bases. For the first example, we can rewrite this as a radical with an index of 4 raised to the 1st power. However, we have an issue because this is a negative radicand with an even index. And since the radicand cannot be negative with an even index, this is not a real number. For the next example, we can rewrite this as a radical with an index of 3 raised to the 1st power. And the cube root of negative 125 is negative 5, since negative 5 quantity cubed is negative 125. We write the next example as a radical with an index of 2 raised to the 3rd power. However, we have a negative radicand with an even index. Therefore, this is not a real number. And for the next example, notice how only 81 is raised to the 3/2. So we can rewrite this as a radical and just keep the negative sign in front. So the square root of 81 is 9, and then 9 to the 3rd power is 729. But with the negative in front, this equals negative 729. So notice how the parentheses affect how we evaluate an expression. The base of this expression is negative 81, while the base of this expression is just 81. So now let's go over what happens when the rational exponent is negative. This takes us back to our exponent rules for negative exponents. Let's refresh our knowledge. So if we have a value a raised to the negative n, this will equal 1 over a to the n. And if we have 1 over a to the negative n, this will equal a to the n. So for example, to write an expression like 2 to the negative 4 with a positive exponent, we take the reciprocal of the base and make the exponent positive. So it becomes 1 over 2 to the 4th, which equals 1 over 16. And we can extend this idea to rational exponents. So if we have a raised to the negative m over n, we can rewrite it in this following way so that we have a positive exponent. So let's try a few examples. We want to rewrite these expressions with a positive exponent and then evaluate. So since we have a negative exponent for 36, we can rewrite it as 1 over 36 raised to the positive 1/2. And now we can rewrite our denominator as a radical with an index of 2 raised to the first power. And then 1 over the square root of 36 is just 1 over 6. And for the next example, again, we can rewrite this with a positive exponent by taking the reciprocal and making the exponent positive. And now we can rewrite this expression in radical form with an index of 5 raised to the second power. So the fifth root of 32 is 2, and then 2 squared is 4, so this simplifies to 1 over 4. For the next example, we could use our power of a quotient rule, where we raise the entire numerator and the entire denominator by the exponent. So we have 125 raised to the negative 2/3 over 64 raised to the negative 2/3. And now we can use our negative exponent rule. 125 will flip to the denominator, and 64 will flip to the numerator, and then we make the exponents positive. And now that our exponents are positive, we can rewrite this into radical form and simplify. So the cube root of 64 is 4, and the cube root of 125 is 5, and then 4 squared is 16 over 5 squared, which is 25. So we have 16 over 25. Okay, let's try combining our rules that we've learned in this video with the rules of exponents. So for this example, we want to simplify completely and write our answers with positive exponents only. So for this, we can use our power rule and multiply the exponents. So this is 6 to the 2/5. And then we can rewrite this into radical form with an index of 5 raised to the second power. However, the fifth root of 6 will not be a rational number, since there is no integer raised to the fifth power that will give us 6. So if we take the fifth root of 6 on a calculator, we get this irrational number. So we can just leave this as a radical in exact form. For the next example, we can use the product rule of exponents and add the exponents while keeping the common base. So 3 over 4 plus negative 1/4 is 2/4. And then we can simplify this rational exponent as 1/2. And now we can convert this expression to radical form. So the square root of 25 is just 5. For the next example, we can use our quotient rule and subtract the exponents. And then we can simplify negative 9 over 9, which gives us 8 to the negative 1. And using our negative rule for exponents, we can write this as 1 over 8 raised to the first power, or simply 1 over 8. Now let's try some examples of expressions with variables. So for example 5, we want to simplify completely and write our answers with positive exponents only. So for this, we can use our product rule and add the exponents while keeping the common base. So we get x to the 4/8, which can be simplified as x to the 1/2, and then rewriting this as a radical will give us square root of x, which actually can't be broken down further, so we can just leave it as square root of x or as x to the 1/2 power. And for the next example, we can use our power of a quotient rule to raise the entire numerator and the entire denominator by the power of 6. And then using our power rule, we can multiply the exponents and then simplify these exponents. So 12 over 3 simplifies to 4, and 6 over 4 simplifies to 3 halves. And it looks like we can't simplify further, so we can leave this as our final answer, or you can write it in radical notation. So some radicals can be simplified by first putting them into rational exponent form and then converting them back to radicals. So for the first example, you could simplify 9 to the 4th power as 6,561 and then calculate the 8th root of this. The 8th root is actually 3. However, there is a simpler way. We can use this relationship between radicals and rational exponents and rewrite this radical as 9 raised to the 4 over 8. And now we just have to simplify the exponent. So we have 9 raised to the 1/2, and then rewrite this back into radical form as the square root of 9, and the square root of 9 is just 3. For the next example, we can rewrite this radical into exponential form as x raised to the 4 over 6. And then we can actually simplify the exponent. So we get x to the 2/3. And then we can rewrite this back into radical form. So the 6th root of x to the 4th power simplifies to the cube root of x squared.